You train a model, split your data 80-20, and measure how well it does. One split hands you 84%. You reshuffle, split again, same model, same data, and now you get 79. Nothing changed, but which rows happen to land in the test set? So which number do you report? Here's the honest answer. Neither, on its own. A single split is just one sample from all the ways you could have carved the data. Get an easy test set and you look great. Get a hard one and you look poor. The estimate is noisy. It swings with luck. What we want is a number that doesn't depend on one lucky draw. That is exactly what cross-validation gives us. Test on every row, in turn, and average. Before we build it, we need to be clear about three jobs your data has to do, because mixing them up is where people leak information and fool themselves. So we split the full dataset into three parts, not two. The biggest slice is the training set. This is what the model fits, where it learns its parameters, its weights, its coefficients. The second slice is the validation set. This is where you tune, pick the hyperparameters, compare candidate models, decide how flexible to let it be. You look at it many times while developing. And the last slice is the test set. This one is sacred. You lock it away and open it exactly once. At the very end, for a single unbiased estimate of real-world performance. Tune on it, even a little, and it stops being honest. Cross-validation lives inside the validation job. It's a smarter, sturdier way to do that middle step, squeezing far more out of your data than a single fixed validation slice ever could. The test set sits untouched the whole time. Here is the idea that makes it work. And it's beautifully simple. Take the data you'd use for training and validation and cut it into k equal-sized blocks. We call each block a fold. Let's use 5. Now the rotation. In each round, we hold out just one fold as the validation set, train the model on the other 4, and record its score. Then we rotate. A different fold takes its turn. Watch the validation block move along the bar. Round 1. Fold 1 is the validation set. It lights up. Folds 2 through 5 are training. Train, score on fold 1, 0.80. Round 2. Now fold 2 steps into the validation role and fold 1 rejoins training. Retrain from scratch, score on fold 2, 2.85. Round 3. The held out block slides to fold 3. Retrain, score 0.82. Round 4. Fold 4 is held out now. Retrain, score 0.88. Round 5. The last. Fold 5 takes its turn as validation. Retrain, score B0.85. 5 rounds, 5 scores. The cross-validation estimate is simply their average. Add them. 0.80 plus 85 plus 82 plus 88 plus 85 is 4.20. Divide by 5 and we get 0.84. That one number, steadier than any single split, is our verdict on the model. In symbols, for k folds, the cross-validation score is 1 over k times the sum of the k-fold scores, just the mean. People also report the spread of those scores, the standard deviation, as a measure of how stable the estimate is. So why is this better than one split? 2 reasons, and they're worth seeing clearly. First, every single data point gets used for validation exactly once, and for training in every other round, k-1 times. Nothing is wasted. Second, and this is the real prize, averaging over k-folds smooth out the luck of any one split. A single unlucky test set can't dominate. It's just one of 5 votes. So the cross-validation estimate has lower variance than a single holdout. It sits much closer to the model's true performance. So what should K be? The honest answer, 5 or 10, almost always. They're the practical sweet spot. Turn K up and each model trains on more data, which is good. But you also train more models, which costs more. Turn it down and it's cheaper. But each fold sees less data. 5 and 10 balance that trade nicely. Push k all the way to the extreme. Set k equal to n, the number of training points, and you get leaven out cross-validation. Every fold is a single point. You train on all but one, test on that one, and repeat for every point in turn. Leaven out is nearly unbiased. Each model trains on almost all your data. But it has two real downsides. It's expensive, n points means training n whole models. And its estimate is high variance, because each test is a single point. Every score is either right or wrong, 0 or 1. For most work, 5 or 10-fold is the better deal. One more variant you'll reach for constantly. Suppose your classes are imbalanced. Say only 5% of your samples are positive. A plain, random split might, by bad luck, leave a fold with almost no positives, and your score goes haywire. Stratified k-fold fixes this. It builds each fold to hold the same class proportions as the whole set. Where do those numbers come from? Take 900 training rows at 5% positive. That's 45 positives and 855 negatives. Split into 5 folds of 180 each, and stratifying puts 9 positives and 171 negatives in every fold. For skewed classes, stratified k-fold is the sensible default, often paired with a metric like ROCUC instead of raw accuracy. Now the payoff, what we actually use cross-validation for, choosing hyperparameters. Think of ridge regression, where a knob called lambda controls how hard we regularize. Too little, and the model overfits. Too much, and it underfits. Which lambda is best? We don't guess. We let cross-validation decide. Here's the recipe. Lay out a grid of candidate lambdas. For each one, run a full 5-fold cross-validation and get its average validation score. Then simply pick the lambda whose score is highest. Let's run it. 5 lambdas from 100th up to 100. Each row's number is itself a 5-fold average. Read down the column. At a tiny lambda, the model barely regularizes, overfits, and scores just 0.79. Crank lambda up to 100, and it oversmooths, underfits, and drops to 0.81. And in the middle sits the winner. Lambda equals 1, with the highest score, 0.90. That's the sweet spot the cross-validation found for us. Enough regularization to tame the variance, not so much that we lose the signal. Two crucial steps remain, and people forget them. Once cross-validation has picked lambda equals 1, you refit the model one final time on all your training data together. Every fold combined, nothing held out anymore. Then, and only then, you open that sacred test set, once, to report an honest final number. Your turn. Pause the video and work it out before I do. You ran 5-fold cross-validation and got these 5-fold scores: 0.90, 0.86, 0.88, 0.84, and 0.92. What's the cross-validation estimate? I'll wait. Here's the working. It's just the mean of the 5. Add them up. 0.90 plus 86 plus 88 plus 84 plus 92 comes to 4.40. Divide by 5. And the cross-validation estimate is 0.88. If you got that, you've got the core of the whole method. Trap 1. The cardinal sin. Never tune on the test set. That is precisely what the validation set and cross-validation exist for. The test set is opened exactly once, right at the end. Trap 2. The sneaky one. Do your pre-processing, scaling, imputation inside each fold, fitting it on the training folds alone. Scale using the whole set first, and information from validation leaks into training. Silent, and it inflates your score. Trap 3. In k-fold, k is the number of folds, not the number of points in a fold. Each fold holds roughly n over k points. Trap 4. Leaven out sounds ideal, but it's expensive and its estimate is high variance. 5 or tenfold usually wins in practice. And trap 5. With skewed classes, stratify so each fold keeps the class ratios. And remember, once CV picks your settings, refit on all the training data before you test. Let's lock it in. A single train test split gives a noisy estimate that swings with luck. So we cross-validate instead. The cross-validation score is the average of the k-fold scores. Steadier, lower variance, closer to the truth. In k-fold, you cut the data into k-folds and rotate which one is held out for validation. Then average across all k rounds. Liven out is k-fold taken to the limit, k equals n. And for imbalanced classes, you stratify to keep the class ratios in every fold. And the workflow that ties it together. Tune your hyperparameters with cross-validation. Refit on all the training data and open the test set exactly once. Hold that, and you'll never trust a single lucky split again.